So once we start to know lots of these relationships, we can start moving into an area of geometry called coordinate geometry, which basically is going to hinge on two formulas. It's going to hinge on the slope formula, which tells us if lines are parallel or perpendicular. It's going to hinge on the distance formula, which tells us something about length. And sometimes we have to use the midpoint formula if we're looking for middle or intersecting points or things like that. So those three algebra formulas are going to be what you need to do coordinate geometry. So given the triangle below, graph the midsegment MN, which would be parallel to XZ. Verify. This literally means show all work. And your conclusion. If you don't show your work in coordinate geometry, it is not correct. You can't just guess. You can't just say, oh, they are. You have to show the slope formulas to show that they're parallel, to verify that that is true. Meets the criteria of midsegment. Well, what does it mean to be a midsegment? It means you have to be parallel. So we're going to look at slope. And the length has to be half the side it's parallel to. So we're going to use the distance formula. But even before that, we have to find M and N. We need to find M and N, which are those midpoints. So let's start with XY. And let's call that midpoint XZ is where we're supposed to be parallel. And let's call the XY M. Well, midpoint here is 1 plus 5 divided by 2, 1 plus 5 divided by 2, 6 over 2, I have 3, 3. So 1, 2, 3, 1, 2, 3. There is M. And then let's look at YZ, and we'll call that one N. So my midpoint there is going to be 3 plus 5 divided by 2, and 9 plus 5 divided by 2. So I have 8 divided by 2, which is 4, and 14 divided by 2, which is 7. So I have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. So N is at 4, 7, and M is at 3, 3. So this segment right here is my midsegment. Now I need to verify that it's parallel. Which means I have to show the slope of XZ is the same as the slope of MN. That's my plan. That's what my work has to show. So let's find the slope. The slope of XZ, and I tend to use subscript numbers just to keep my work clean. Remember, slopes, we're going to subtract our y's, 9 minus 1 over 3 minus 1. So I have 8 over 2, so my slope is 4. And if you want to do 4 over 1, that's fine. My slope of MN, if I take 7 minus 3 over 4 minus 3, I get 4 over 1. And then what you need to do to verify it, I go like this. I say, therefore, MN parallel XZ because slopes are same. And that conclusion just shows you understood what you found. Now, our next piece is length. And what we know has to be true in a midsegment is that 2 times MN has to be the same as XZ. So that, using the distance formula, is what has to be true. So again, I do the distance and I say MN. I use those little subscripts. So what are our coordinates again? So I have the square root of 4 minus 3, the quantity squared, plus 7 minus 3, the quantity squared. So I have 1 squared plus 4 squared. So I have 1 plus 16, which is the square root of 17. Kind of a weird number, but I'm just going to leave it for now. If I have the distance then of xz, and I find that distance, my coordinates, I'm going to have 3 minus 1 plus 9 minus 1. And so I have 2 squared plus 8 squared. And so I have 4 plus 64, which is the square root of 68. Now, as that stands, you may not know what those values are, but if you go to your calculator, the square root of 17 is approximately 4.12, and the square root of 68 is approximately 8.25. And since I'm rounding, what I can say is, therefore, 2 times 4.12 is equal to 8.25, because I'm rounding. So lengths meet criteria. So you've shown that that criteria is true. So that is a perfect example of the elements of a coordinate geometry proof problem. Tune in to the next video for the last example.